Hello, everyone. Welcome to the LLVM uplink presentation for this talk. So I saw Raj Talluri has, in his keynote, mentioned the LLVM Snapdragon compiler and the importance for improving the optimization for your compiler, for your applications. So the goal today for me is not to talk what the LLVM compiler Snapdragon does or what's its capability, is to help you, developer, and how to write better code that make the compiler more effective at performance, so that you have faster code. The problem is that the hardware has been evolving and putting complex features, and it's not easy to take advantage of them if the programmer doesn't do a little effort to enable the compiler to understand the intent that is in your brain and basically create the most optimal code for the CPU. So the Snapdragon LLVM compiler is available on QDevNet, the Qualcomm Developer Network. It's for Android. It goes on the NDK. There's David Kipping, he's over there. He's our product manager, so if you have talked to him for anything. And there is Raja, who is the lead for the LLVMR over there. So if you have questions, I'm going to be here only today, unfortunately. I have some emergencies. I will be leaving at the end of the day. But if you have any questions, you're welcome to address them to Raja or David. So the Snapdragon LLVM compiler is based on the community LLVM compiler. So we work with the community, we develop, but we also have in-house optimizations that the community doesn't have. And one of the most important one is the vectorizer. The community has a vectorizer, and we have a different vectorizer that's more advanced. So we have proved it with performance. And it's specially tuned for Snapdragon, and especially tuned for the neon instructions to generate the best neon instructions. So if you have any graphic, video, camera, gaming, anything, then you want to take a look at it, and you want to try this compiler. But this talk is not about advertising the Snapdragon. It's about helping you improving performance and writing better code. So what I would do for this talk, I would present some examples. So real examples that I saw over real code that I analyzed in the Android, in applications in-house inside Qualcomm. So I abstracted the test cases to really small because the slide is not enough. And the idea is to explain the problem, but they're real. You see them, programmers repeat them everywhere, and they're not aware that by doing what they do, they're making the compiler ineffective, and they're not taking advantage of the CPU. So over this talk, we'll talk a little bit about compilers in general, not specifically for LLVM or other compilers. So every compiler, every industry compiler will have those pros and cons and everything. And then we'll go through the guidelines. So I think I have about 5 or 6 guidelines, generic ones. Then I would like to talk about the pragma, the new pragma that LLVM is offering for controlling the vectorizer. This is the first set. I'm hoping over the future, the LLVM community will add other pragma that allows the user to control the optimizations and decide which piece of code I want to apply this optimization, or maybe disable it because it doesn't work. It's not helping me. And then we'll talk a little bit about the internal flags. The LLVM has a lot of optimizations that are turned off because they're experimental or they're buggy or I don't know. There's a lot of thresholds that are being set because the goal of the compiler writer is not to support one app, it's support everyone. So we have to find a blended mode where the optimization does best in general. That means for a specific piece of code, you may be adversely impacted because the threshold requires to be higher in order for that optimization to kick in. So the community right now is working on a reporting tool. And the reporting, basically what it does, it will run and it will tell you when an optimization failed to apply. And then it's up to you to modify the code or to add a new flag to the compiler, or maybe one day we'll have a pragma that will say, hey, on this piece of code, do, for example, for the enroll threshold or for vectorization, do this or don't do that, something like that. This is the evolution. So the optimization reporting is a feature that's coming in the community in the LLVM 3.6. And we will follow it with our Snapdragon LLVM and extend on it to make it even better for you guys. Yes?
Do you also get coding guidelines for power?
For what? So the coding guidelines are for performance right now. So, but whenever you improve performance, you improve power. So they are correlating in general. But this is mostly for performance, but I believe it will help power. So. All right, so software has been growing exponentially. I mean, in the 70s, there were the software crisis that the NASA was talking about, and the software is growing so complex, and we don't know how to manage it. And from there, from those 70s to now, I think we have come up with solutions. Tools, developer, and compiler writers in general came up with many tools to support large software development and app development, especially in the space of security, the space of software quality, like finding bugs, finding problems. So in the LLVM, the community is very actively working on that. You can find the static analyzer. Basically, it's a tool that looks for semantic errors, not just syntax errors. So basically, if you forget an initialized variable, it will find it. It will tell you, hey, there is something here weird that should not be, because it will check the invariant properties of the program. So I recommend use that. There is also the address sanitizer that checks the pointers and the memory, and if there is anything that double free or double think or even there is leak analysis and all that to help the user to improve the quality of the software and support your customers in the best way you can. And then there is also coverage tools which allows you to test better, so that you verify how many paths are being verified by the tests you guys are creating while writing your software. So all those tools are really great, and I really encourage everyone to look into them, use them, and report feedback. On the performance side, unfortunately, little effort has been done. So basically, over the history of CPU and all, CPU has been improving. It's been shrinking. It's been lifting the boat of performance by about 20%, I would say, every generation in the past. That's not anymore true anymore, because we're reaching some level of technology, we're reaching some threshold where the CPU will not do the magic just because it's going to happen. So suddenly we do multi-core, we're adding new features, we're adding CMD, we're expanding the vector instruction. Things are getting more complex, but in terms of tools to help developer to track performance or understand, it's really ad hoc right now. So the best thing people say when I try to hire someone, ask him, how do you analyze performance? First thing, I'm going to profile. Profile what? I'm going to profile and see how the hot function, and then what if there's no hot function? What is this flat? What are you going to do there? I don't know what to do. So most of the even advanced compiler writer or PhD who comes to, they get stuck. They don't know how to address performance or how to nail it down, to pinpoint what's the problem, why the hardware is not delivering the performance, and what should we do. Most of the time, developer end up rewriting the code in using either C intrinsics, which are basically low-level code, or writing assembly, or doing something really weird, wrong probably, to avoid the problem, right? So basically, there's no help. There's very little help that most developers have to look at performance. That said, the compilers have evolved quite a bit along with the hardware. So today's industry compiler, you can look at LLVM, I would say over hundreds of optimizations are available that are really advanced and active, trying to understand the code, trying to simplify it, trying to optimize it in the best way. A lot of research has been going at developing advanced optimizations like this vectorization, which tries to target the CMD execution unit. or for multi-core auto-parallelization, yeah, there is OpenMP. There is a lot of effort trying to leverage the power that Snapdragon CPU can offer. On the other hand, you, as developer, have a high expectation of compilers. You expect compilers to be perfect, to work on every program. And that puts huge amount of constraints on the compiler writer in being extremely conservative. So basically, if the compiler cannot prove that it's correct what it's doing, it will bail out and it will generate poor code. That's the policy of every compiler writer. If I cannot prove the transformation to be legal, I'm not going to do it, because the user, my customers, want me to be correct all the time on every point, on every input scenario, and whenever there's a compiler bug, it's always something like the end of the world. It's like, oh, how can compiler can be wrong? No, that's not. I have to trust it. So this puts a lot of constraint, and this is the real priority of a compiler writer. He looks at performance as a secondary, correctness. So we test the compiler heavily all the time. We look at, we test like a huge amount, millions of, it could be 100,000 of code. I mean, if whatever code we can find, we try to run the compilers to validate it, to make sure that you guys can trust it and can run on it. The second one is, of course, the compiler is dumb. It's not producing efficient code. So a lot of time, the blame goes always on the compiler. So you talk to programmers, even in-house inside Qualcomm or outside. Most of the time, a compiler is not smart. It's not doing this. It's supposed to do that. But most of the time, the programmer forgets that on one case, it doesn't work. It works on the case that you have in your brain, but you didn't express it correctly. So there may be extreme, rare cases where the transformation you had in mind is not legal. It will generate incorrect program. So a lot of time, that way I get a bug, I look at it and say, well, I cannot do it. If I do this, then, give me an unsafe flag, or give me some flag that can do that. And most compiler writers are not comfortable at giving unsafe flag, but we do that sometimes just to enable our customers. So the expectations are high. And unfortunately, a lot of developers fails to understand that compilers are really programs. And they have thousands of bugs in them because they're large, they're big, they have bugs, they don't work, and often if you have a large software, you run into a GCC bug or LLVM bug, and you know that it's not your application, you know that it's the compiler who's producing the incorrect code, and you have to keep it in mind. The other thing that you have to understand is that there's no expectations or no assumptions of what the compiler will optimize, because that optimization are limited. When we designed it, we took some trade-offs, or we had time constraints, we didn't enable it fully. So that specific code that you have, it will not be optimized the way you expect to be optimized. And then other times, sometimes we don't have that optimization at all. We didn't have time to implement it. So the compiler lacks that optimization that you thought is going to be there to optimize the code that you have. So really, there's no expectation. You really have to go and inspect the code and say, did it do it or not? I mean, is the performance is there or not? So that's the reason why it's important to write the code in the way that you write your intent and you simplify the code so that the compiler handle the most simple case, the cases. And through the guidelines, hopefully I will give you an overview of what I mean by that. There is some hope. There is some hope for us, and as I said, a minor rewrite sometimes of your program, and I'm not advocating that you make your program unreadable or you write it in a weird way or something. No, most important for me, I understand the priority is to keep the code maintainable and simple. So, but minor rewrite could make significantly the compiler effective at applying an optimization that will multiply the performance by 2-digit or more by many factors, especially if you enable a vectorization instance or you enable parallelization. Those performances are pretty powerful. If that loop is very hot or that piece of code is extremely hot, then you will see benefit from it. The other things which I'm hopeful is the reporting tools. So hopefully you guys, because right now you're in the dark, most of programmers are in the dark, they don't know what the compiler really did. Now with this feature that's coming, the community is working actively and we are contributing with them, we're looking and extending ourselves, is that you will have remarks. So the compiler now emits errors, emits warning, it will emit remarks. Those remarks will tell you, hey, I didn't do this because of that. So this optimization did not appear for that reason. So watch for the LLVM 3.6 that's coming end of this year. Sometimes I think our Snapdragon LLVM around December or maybe January, around that time frame, we should be releasing a new compiler that I'm not promising that it's going to solve all your problems, but hopefully you will have the first iteration of this feature, and it's going to evolve over time. So give it some time. We're looking forward to report bugs and report issues, and we'll fix them. And over time, it will mature and then get something useful to you guys. So now, the guidelines, as I said, I wrote them in simple toy loops. So it may look ineffective, but I can tell you that by doing some statistics, looking at various C code that I see, they're there. So all of us, we do that, and we assume that somehow the compiler will magically do what I expect, but it will not do. Before we go into the guidelines, there is this. So hopefully you read it all. So it's the license that our legal allow me to present this data. So it's BSD license, so it's available to everyone. I don't know where it's going to be available, but probably David can update you later if you want to review those examples. So the first guideline I have is, the question I ask is, how many iterations this loop executes? Can someone tell me how many times this loop executes? And the answer, of course, we don't know. We don't know, because that function, that's right. We don't know what compute_n does, and compute_n is executed every iteration of the loop. And it can change, the value that is returned by compute_n can change over the execution of the loop. Imagine that compute_n return A5 or A4. Then A4 will be changing, which means the number of iterations will be changing over the execution of the loop, right? So you write like this, you put some complex end loop. Unfortunately, in C, the end is executed all the time. Every iteration is going to reevaluate compute_n. And if it gets modified while the loop body executed, then now you change the number of iterations. So this is a bad idea. The compiler will just bail out on this. It will do nothing. It will not vectorize, will not optimize. It will just generate the plain code the way you write it. A simple change, like this. You hoist the function call outside. Since you know that in your brain, you know that it's n, it just, you know it's not going to change over the execution of the loop. You are the domain expert. So put it into a local variable, put for 0 less than n, and you know you will give in valuable information to the compiler that this loop is executed n times. Once the compiler knows this loop is executed n times, and of course it's going to inspect the loop body and make sure the loop body is safe also. If everything works well, it's going to generate some check, say if there is at least 4 or 5 or whatever iteration needed, I'm going to SIMD this loop, in the sense that I'm going to execute 4 iterations in one time using the neon instruction, using the SIMD instruction. Or maybe I'm going to parallelize this loop. I'm going to check if n is more than some threshold, then I'm going to split the loop into 4 mini loops, create threads, run them in parallel, return the value for whatever the compiler decides, it will generate for you. You write the previous program, the program on the left, then what happened? You don't get the optimization. Well, you thought that it's going to be there. It's not. Okay?
So you're saying that the one on the left is inefficient, unsafe, or both?
The compiler is conservative, right? It will do nothing. It will not try to SIMD this loop or try to parallelize this loop or try to do anything with it. It will just generate it the way it sees it, and it says, I can't figure out how many iterations this loop is executing. I'm not going to take any risk. I'm just going to generate the code the way it's written, and that's it. So you will not have high-performing code because of that, while a minor change like this will give you the performance that you wanted to get from this loop. Okay? Doesn't matter whether it's a while loop.
Basically, you could get a conditional instruction. So use, sorry.
Yeah. Thank you. Sorry, I forgot. Yeah, use a microphone so everyone can hear.
So basically, the reason why I say we could use while loop to optimize is while loop, when you do while n minus minus, then you have conditional instruction. When it becomes 0, you don't need additional instructions, and you could optimize int also. Yeah.
That doesn't matter for the compiler. If the compiler will always optimize it into a while, do while. So
yeah.
When you have a loop, the compiler will do that for you. So that's not a concern. Whether you write it in while or for, or you write it, the compiler will always check first, do the body, then do the condition and loop back. That's why the backward jumps are predictable by default. The hardware will predict them. That's not. If you want to do that, that's fine, but it's not necessary. The compiler is smart at transforming the control flow in a way that you have that.
If the compiler is doing under the hood, if it's converting
Yeah.
to while, then
Yeah.
I think it's achieving what I wanted to achieve. So it's okay.
Yeah. Yes. So the most important is that you give. You're welcome. So the most important is that you give the compiler that this loop is executed n times. That's the most. So it knows how many iterations this loop is executing, so that it can optimize it the way you're thinking. So the SIMD or enroll or loop software pipeline, all those loop transform that we like, and then they help hardware. They create instruction level parallelism. They create the parallel, because remember, the hardware has multiple execution units. It needs parallelism to run faster. You need to create the parallelism in the code. This is sequential code, but if you give that information, the compiler will do whatever needed for that hardware. For Snapdragon, it will try to, for the LLVM, the core ARM, it will try to vectorize it. If you write for DSP, which we have LLVM DSP, then it will do software pipelining to create parallelism. Whatever, the compiler knows what it needs for the hardware. You just need to give it the hints so that it can optimize it. And that's the hint. It's an iteration. It's not, I don't know. All right? Let's go to the next one. This is another loop. So this loop looks to be, hey, it looks like an iteration. Is it really executing an iteration, this loop?
What's the question?
Is this loop executing an iteration?
N by 2.
And is it n by 2? Anyone else? And the answer is no. There's one case. What if it overflow? Right? You could create this loop, it become an infinite loop. And in C standard, unsigned type has to consider overflow. So the compiler has to be aware of overflow. I mean, some compilers may optimize this because they will check that overflow is not possible. It will verify that. But a lot of compilers will not. We'll see unsigned, they will just bail out and not optimize this loop. Because you use unsigned, overflow is possible. This loop could be infinite or could be n divide 2, then it's not going to optimize it. So you will not get the optimization. So you have to understand there is a difference between signed and signed. It's not just about the sign. Unsigned, the semantic is well defined for the overflow. So you have to optimize for the overflow. It's defined. While if you use signed type, signed int, overflow is undefined in C semantic, which means that you could consider it n divide 2. So if you know that overflow is not a concern for you, it doesn't matter overflow, then use always signed. Don't use unsigned type. And more importantly, I don't have guidelines, but I will say it to you, don't use short or char or use int. Int is the most optimized type in the compiler. So there is two types that are where the compiler does best, int and char. Short is depend on the domain. If you are writing for DSP, short is important. But a lot of times short doesn't appear in software a lot. So it will not be optimized. Don't worry about saying, oh, I'm using short, I'm saving memory, or I'm saving a register, or you're not saving nothing. The register is 32-bit always. You're saving 0 there. You're just creating trouble to the compiler to understand it, especially if you mix between short and int. And I see that. You see the user will put short I equals 0, I less than n, and n is an int. So suddenly now you're mixing short, which is 16-bit, and you're mixing n, which is 32-bit. And in that case, we don't know how many iterations, because we have to consider that n is larger than 2 to the 16, and in that case, the loop is infinite. It's never going to end. We will bail out. So the compiler will say sorry. So you lose the performance. Make uniform type. Loop trip count most of the time is int. So unless you worry about, you care about the overflow, I mean, you want to have overflow some. I've never seen a lot. I mean, I've never seen anyone cares about the overflow. But if you are some numerical guy and then you want to worry about the overflow, then yeah, use unsigned, of course, in that case. But int, and you'll be okay. Compiler will assume it's n divide 2 iterations. It will vectorize. It will do whatever is needed to target your CPU. All right? So let's look at another guideline. So this one is very, very frequent also. So user define a data structure, a large one, and then the trip count of the loop is usually a field in that data structure. Right? A lot of time you see that. I mean, it makes sense. You want to encapsulate everything in one data structure. So when you get to execute the loop, you say, hey, I know the trip count I need to do, s to the n, and then you do that. The problem, do we know the trip count of this loop again? And again, we don't, because the compiler has to consider the potential that b of I, one of the elements, could point to that n, to the number of elements of the loop. And in that case, we don't know how many iterations the loop is executing, and the compiler has to bail out to preserve correctness, because we want correctness all the time. So we will not optimize it. So a simple, it's similar guideline, a simple hoist of data structure. And the reason why I'm insisting on the trip count and all, because that's the first thing the compiler will check when it sees a loop. It will check, can I figure out ahead of time how many iterations this loop, whether it's compile time, which I know it's 100, or whether it's n or something. Can I figure out a mathematical proof that it's executing this number of iteration so that I can parallelize or do whatever it's need to do? All right? So another one.
I have a question.
Of course.
The previous one.
Yeah.
So here you say n equal to s of num element. So do you mean to say that the compiler statically figures out what s the num element field computes to before runtime?
No, the compiler manages it as a symbolic question. Yeah, let me repeat the question. So he's saying, does the compiler know how many real iterations they're going to be? No, that's at runtime we will know. But the compiler knows that the value is held in that variable. So you can check that variable. So if I need at least 4 iterations, I can generate a check. If this value is greater than 4, then I will vectorize the loop. Else I do. I can do reason about the number of iteration in a symbolic way. Right? I don't need to know the exact number. What I need to know, where is it being held? Which variable contains that value? And in this case, it will be n. Right? N contains the trip count of that loop. Right? So I can generate a check. I can produce an if n greater than 4 or n greater than 1,000,000, then I will parallelize, because I know there is at least 1,000,000 iteration. Right? Compiler will generate control flow, will generate if, then else, it will generate that loop. Some of the loop I can show you in the assembly, it will expand to pages of assembly code, because it has so many versions of that loop. If the trip count is small, if there is aliasing, if there is dependence, if there is this, it will generate various paths to get. In order for you, when those conditions are met, you will have the best performing loop. Right? So that's what we call versioning in compiler jargon. So
the address for n gets below.
yes, so we need to know n. We need to know, of course, the compiler see that variable and say, hey, the trip count is held inside n. So I can reason about n. I can generate checks and things and then make sure that every scenario is well optimized for it. Okay? Yes?
If I know that n is always going to be between, say, 10 and 100, can I tell the compiler that so it can reduce the code size?
So in some compilers support that. It's typically called assume in Microsoft compiler. So assume n or something, so that you don't generate multiple paths. That's what you want to do. So that exists. LLVM doesn't have that yet. So it's evolving. I imagine that it's going to happen over time, but this is a community compiler. A lot of people are involved. Every time there is a new addition that is visible to the user, there's huge debate. It takes time to agree, come up with an abstraction and a syntax that, okay, this looks to be reasonable. So it will come eventually, but we have not, in LLVM we don't have. Other compilers, yes, they do have that. Say n is not 0, so don't consider case 0, so you're safe. And then you take the risk, of course. If you execute and n happen to be 0, you're going to have an incorrect program, and that's at your own risk as a developer.
If the value of n mutates inside of the for body, can it still be optimized?
It cannot mutate in this case. So n is a local variable, and it's anonymous. Nobody took the address of n. So there's no way that n can mutate while loop is executing. Right? In order to mutate it, someone needs to grab its address and pass it to somebody else, and then you can have a pointer aliasing, and then somebody will side effect it. But right now, it's anonymous. It's a local variable. It can live in a register. It doesn't have to live in memory right now. It's a local variable. Every local variable where you don't dereference, you don't use the end, you know, the addressing, right? The end operator. If you don't use the end operator, that means it cannot escape. That means it's anonymous. No pointer can point to it. Right? So you can live in registers. It doesn't have to be real. Okay, let me move further. All right, so let's go to the next one. And here, another interesting loop. This is not about trip count anymore, but you have some complex indirection, right? And this indirection, again, create aliasing. And because of that, there is likely not ability to parallelize or vectorize this loop, because the compiler will start to say, what if there is a circular pointing, right? This indirection point to this, and then circular. So basically you have a circular indirection. So it's going to say, oh, hey, I cannot make any assumption here. I cannot optimize this loop. I mean, some compiler will generate some checks to optimize it, but a lot of compiler will not. And it's too, because the checks are expensive, it's going to blow the code size. So we will not do that. We will just bail out. So a simple rewrite will do, basically you hoist the invariant, which is SROB, and you use it with the pointer. Yeah, basically complex indirection is more than two-level indirection. So int star star, int star star. So basically you have multiple complex address calculation, a lot of indirection. So you hoist the address calculation that you know that it will not vary during the execution of the loop. You hold it into a pointer, and then you use that pointer directly. That means the compiler will understand. You will be able to optimize. You will not worry about aliasing problems. So the biggest problem of C is that pointer point to the same object, right? Then there is side effect, and it will create incorrect programs. So a simple rewrite like that will make sure that there is no aliasing between the pointers, right? So you see, AROB is one indirection, and then bracket I is another dereferencing of a pointer. So it's two-level, it's int star star, right? It's a two-level pointer. This is better to hoist the part that you know is constant. The compiler will not do it for you, unfortunately.
So a two-level, so the one on the right is a two-level pointer?
So B is a two-level pointer, int star star.
Okay.
Right. So it means that B of I could be pointing to A of B, and the compiler will not go. So a lot of time, even a compiler expert, even somebody who spent years, it's hard for him to figure out why the aliasing happens. Because C is so ambiguous and so complex that it's best as a developer, as a writer, as a domain expert, you understand what you're doing. You just spend things, say, hey, let me hoist this address calculation. Let's make sure that I'm doing the simple things for the compiler, basically accessing the int star, the one-level indirection. Let me get some interesting, easier ones that I see also. So this one is easy. So basically here you have A and B, and again, the compiler would not try to parallelize or vectorize this loop because A and B could be the same array, right? They're pointers. They could be pointing the same array. There's one case where basically A point to BI plus 1. And in that case, it would be incorrect to do any parallelization or anything. So if you know A and B point to different objects, then there is a keyword in C, the restrict. Everyone knows that one. To say that, look, A and B are different arrays. There is no way that they point to the same array. And in that case, the compiler will take freedom to do a lot of optimization and optimize the code that you guys have. The next one is kind of interesting. So basically here, the user wrote, I made it complex because this is a real thing that I saw in real code. And basically the user wants to specialize for the first and the last iteration. So he wants, when it's the last iteration, do something else. When it's the first iteration, do something else, and then the common case, do that. I mean, maybe it's useful, maybe it's readable to your brain, but to the brain of the compiler, this is complex control flow. A lot of times, some compiler may be smart at getting, but most compiler, even best compiler out there, GCC, LLVM, they'll just do nothing. They'll just generate the code the way you wrote it. A simple rewrite, why don't you just hoist the first iteration outside the loop, hoist the last iteration so that you capture the common case. In the common case, you basically want to do A and 15. That's what or 15. That's what you want to do. That's A or 15 execute n minus 1 times m minus 1 times. It's the most common. It will be the hottest loop in the program. That's your hottest loop. So a simple unwinding of the loop can do that. A lot of compiler may be able to do PIL, but when you look at 2-level nest loop or 3-level nest loop, it becomes harder and harder for the compiler to understand all of that complexity. While you, as algorithm writer, it's obvious to you. Say, okay, for 0, I want to do this, or I do this 0 first. Don't put it inside the loop. And then for n minus 1, then do the n minus 1 case outside the loop, and then keep the common case separate. You will create a much simpler loop that the compiler can optimize very easily and generate the best performance. If this loop is hot and you know it's hot, it's very frequent, spend a little effort to write it better instead of using the spaghetti code, the control flow here and there. That will not be helpful. Okay? So this ends the first set of guidelines. I hope that this kind of gives you thinking about how the compiler thinks. It's different from how the programmer thinks, right? So there is a gap there. And hope we'll have some more. I mean, maybe a document in the future or something to kind of give more what to look for to write for performance and how to write a better software that generate the fastest code while keep it readable and manageable. So the guidelines I showed are minimal rewrite. I'm not trying to make it obscure or make it worse than what it is. All right. So now we go to the next section, the pragma. So I would like to introduce the first set of pragma that the LLVM has. It's for auto vectorization, so basically targeting the neon. So the community is very active at doing the auto vectorization right now. We have a separate auto vectorizer that we put in the LLVM Snapdragon. We make that decision so that we can best target the Snapdragon CPU. So here's the scenario where you want to tell the compiler, don't optimize this loop. So for example, the user knows this loop is very infrequent. It executes like 2 or 3 iterations. The compiler is not smart. Does not have math inside. It didn't take a degree of math like you guys. It doesn't know that n mod 4 is at most 3. It may be more complex. That n mod 4 may be somewhere else, defined in another function or in another file. So there's no way for the compiler to know that this loop is infrequent. No point in do the optimization and take more compile time, take more make it more complex, because when there is too few iterations, auto-vectorization can be detrimental for performance, because you need to check whether you have at least 4. You need to add all the checks to verify that. So all we do is something simple. You write, this is the syntax that the community decided to choose. You write pragma clang loop vectorize disable, and the compiler say, okay, the user giving me hint, don't touch this loop, just skip it. And the compiler will skip this loop. There will be no auto-vectorization that will occur for this loop. Right? This is a scenario. So if you know loops that are infrequent or something, you want to make sure that you give that information to the compiler. Another scenario here, another code that I have here, for example, is here basically you know that this loop has at most 14 iterations. So it's infrequent, but not that infrequent. So if you let the compiler vectorize this one, because it's a char, which is 8-bit, and the register size is 128-bit, so it's going to vectorize it with 16, because it's going to say, I'm going to fill the whole vector register, and you need 16 iterations. So it means that you will never take advantage, because here you have 14 iterations, so you're not going to take advantage of the SIMD code. So what you do, you can write a pragma and say, hey, don't go over 8, so use 8. So vectorize up to 8, which is sort of half register, and Neon support half register, which is the D registers in the Neon. So basically, the compiler will take advantage only half register. So you will do 8 iterations simultaneously, and then you do 6 after that. You do the 6 iterations that are left over. And you still can benefit from that. You still can speed up. But if you let the compiler blindly optimize it, you will try to do 16, and 16 you basically never execute that vector code. So you never take advantage of vectorization. So the pragma gives you a way to scale down the vectorization to a factor that it will be beneficial for you. Another scenario, imagine you have a code, and then you're sensitive about power, and you're sensitive about code size, and you're going to compile with -OS, right? But there is a hot loop. There is a loop that's hot. And when you compile with -OS, the auto-vectorizer is turned off by default. So you will never vectorize any loop because you're compiling with -OS. I don't know, does everyone know what -OS is? It's an optimization flag that compiles for size. And when you compile for size, you don't do those advanced optimizations, the vectorization or enroll, or you don't do those aggressive optimizations for performance. But still, sometimes you have a loop that you know that is preferable. It will gain you maybe 5-6% or maybe even more. So what you do, you put pragma vectorize, force vectorization on this one only. And when you put that pragma vectorize, pragma clang vectorize, it will, even in -OS, even in the lower optimization level, it will turn in that optimization on that specific loop and optimize it for you. So that's a neat feature. That's a very good feature to kind of squeeze a little bit more performance while using a lower optimization level to take care of power and code size, most importantly. All right, these are the use scenarios that the community has done. Those pragmas are well documented. You just do a Google over Clang LLVM, you'll see all the syntax. They're well explained and all. And then the next slide, so I have one slide for the internal flags. So the internal flag are sort of backhand flags. They need to be prefixed with -MLLVM and then dash something. To see them, you need to do clang. You need to do clang help dash hidden. And they'll be printed and they'll have some description. It's not well maintained. This is not for beginners. This is really for the advanced programmer who understand compilers and understand a little bit what's going on. So basically, as I said before, the compiler has a set of optimizations. It enables a blended mode. Basically, it will use some heuristics and some thresholds that works well on a set of benchmarks, and the compiler writer will tune it. But many times, your specific code or your specific loop or your specific function or whatever, that threshold is not enough. It needs to be increased so that you get it, right? And unfortunately, most of developers, they don't know, so they go rewrite the code in assembly or something. While they're just increasing that threshold, will trigger that optimization, auto vectorization or anything, will trigger that optimization, and you'll get it for free by just doing that. It's kind of hard because when you change that threshold, there'll be bugs. It's not tested, it's not validated like the blended mode. So there may be risks at bugs, there may be not working properly, so you have to limit it to that smallest piece of code possible. And it has to be important, it has to be very hot for you, it has to be, if it's not a very important piece of code, then who cares, right? So in the future, so right now we're working on this optimization report. What I'm thinking is to make the compiler suggest to increase the threshold for you. So to put a remark and tell you, hey, why don't you increase the enroll threshold and you'll get it, or increase this threshold, use this flag, and you need this, at least this threshold to get it, and then you just go and then you turn it on for that specific function. You have to be aware that I understand that your files may be very large, has 10,000 lines or 2,000 lines, and then extracting that loop into one file and all is complex. I think that there will be discussion in the community to try to see whether we can put pragma or something to control those thresholds, maybe. But right now, we're not ready for that. But just, if performance is important to you, if you really care about, this is an option to consider and to experiment with. So, all right. So to summarize for this talk, so basically, coding guidelines are can increase the effectiveness of compilers. And this is just a sample that I show, like 6 but there's probably hundreds of them, but they're pretty simple. So it's just common sense. It's just trying to make sure that your intent is well written and not ambiguous to the compiler, so that it can infer the right thing, right, and do the right thing for you. The next thing is make sure not to get the right message from me. Keep your code readable. That's more important. Keep your code simple and readable. Don't try obscure things or something. So just if you need to hoist something, no, that's fine. I mean, that's the code remains readable. But in rewriting, I've seen some weird changes that are bad. So try to use common sense and be aware of the compiler, that it needs to understand what's your intent. So when you write, keep that in your mind when you write your code, especially when you know that you're working on a piece of code it's hot. You know that you're the domain expert. You know this will be executed a lot. So you focus on that. You make sure that you write it, because it will save you time later while the performance is not met and your manager is after you. What can you do for it? It will save time. So you invest now a little bit at thinking about that hot piece, and you can save time for yourself in debugging it, in profiling it, and in trying to understand why things didn't work the way it's supposed, and maybe trying to rewrite in a weird way. Just be aware of that. And then the last one, hopefully made you aware of the pragma, so it may be useful to you guys to kind of go and see what you can do with them, try to squeeze performance, and most important is download the Snapdragon LLVM and give it a try. So it may give you free performance for you guys. With that, I think I thank you, and I don't know how much we have for questions.